Hello, today I'm going to be speaking about methane capture technology as a form of climate engineering. Methane capture is a geoengineering strategy aimed at reducing atmospheric methane, which is a potent greenhouse gas with a global warming potential that is approximately 80 times greater than carbon dioxide over the same 20-year period. And this is according to Camille Bond in the Scientific American. Methane emissions originate from various sources, including oil and gas operations, agriculture, landfills, and natural processes like permafrost thawing. Capturing methane presents significant challenges due to its low atmospheric concentration, being about 200 times less than carbon dioxide, and its chemical stability, which makes it resistant to conventional capture methods. Jack Leonard, director of Reducing Emissions of Methane Every Day of the Year program at the U.S. Department of Energy, explains that, quote, CO2 you can capture from the air or you can capture from flue gas because it has a chemical structure that allows you to kind of put a hook on it, but the methane molecules do not. And so capturing methane is very, very difficult, end quote. Consequently, most current technologies focus on oxidizing methane into carbon dioxide, which, while still a greenhouse gas, has comparatively lower immediate impacts on global warming. One approach involves the use of zeolite minerals, which can trap methane in their structures and facilitate its oxidation. Um, According to Desiree Plata, a professor at MIT, zeolites are, quote, efficient at converting methane to CO2, which downgrades the gas's global warming impact, end quote. Despite these innovations, the deployment of methane capture technologies is limited because further research is necessary to enhance its efficiency and its scalability, as well as its economic viability because it is really expensive. AMRAG, a Swiss company, is pioneering a methane capture project that involves releasing iron salt aerosols, or ISAs, into the lower atmosphere to oxidize methane. The company plans to deploy these particles from decommissioned oil platforms near the equator, utilizing 400-meter towers to disperse the aerosols over the open ocean. This method is aiming to mimic natural processes where iron-rich dust from deserts interact with sea salt, which would lead to the formation of chlorine radicals that break down methane molecules. This is according to the Geoengineering Monitor. The project's goal is to eliminate up to 100 million tons of methane by 2027, which would retire approximately 3,000 participating ships emitting ISAs. 1 year test phase was scheduled to begin 2023 to assess the efficiency of the environmental impact of this approach, according to the Geoengineering Monitor. And AMRAG advocates for the creation of a methane credit market, which would be similar to existing carbon credit systems to incentivize methane reduction efforts. However, the project has raised concerns regarding potential environmental risks, including the impact of the iron-rich particles on marine ecosystems and also on human health. Methane capture technologies aim to mitigate climate change by reducing atmospheric methane levels. However, they may also have unintended environmental consequences. For example, the release of iron salt aerosols, or ISAs, like I said, into the atmosphere could lead to several adverse effects because the particles may absorb sunlight, which potentially causes a warming effect. Additionally, the deposition of these particles into oceans could disrupt marine ecosystems and contribute to ocean acidification. A study published in Nature Communications stated that, quote, the addition of chlorine to the atmosphere has been proposed to mitigate global warming through methane reduction by increasing its chemical loss. However, the potential environmental impacts of such climate mitigation remain unexplored, end quote. Similarly, the use of methane digesters on dairy farms, which convert manure to biogas, has been promoted as a climate solution, but critics argue that these digesters can increase local air pollution, including ammonia and particulate matter, adversely affecting community health. Therefore, while methane capture technologies do have potential climate benefits, it's important that we carefully assess and manage their environmental impacts to avoid unintended harm to ecosystems and human health. The technical feasibility of methane capture technologies would vary depending on the approach. For example, bioreactor systems that utilized engineered bacteria have shown promise in laboratory settings because they effectively converted methane into useful chemicals. However, scaling these systems to handle the large volumes of methane emissions would be a significant challenge. The deployment of ISAs for atmospheric methane oxidation is still in the experimental phase, and the effectiveness of this method in real world conditions is uncertain. And there are concerns about the potential environmental and health risks associated with widespread ISA dispersal. Overall, while some methane capture technologies demonstrate potential, we need to do further research before we start deploying them on larger scales to enhance the scalability and the efficiency as well as the safety for large scale employment or deployment. The economic viability of methane capture technologies has a lot of contributing factors, including the implementation costs, potential revenue streams, and market incentives. High natural gas prices have made methane capture projects more economically attractive as captured methane can be sold as a valuable energy source. And additionally, policy measures like the Inflation Reduction Act in the US have introduced financial penalties for methane emissions, which would further incentivize capture efforts. However, the initial investment and operational costs of methane capture technologies can be really expensive. The construction and maintenance of a bioreactor system or ISA deployment infrastructure requires significant capital, and the long-term profitability of these projects depends on consistent policy support and market demand for captured methane-related products. And therefore, while economic opportunities do exist, they will require careful financial planning and supportive policies to ensure that they can be sustainable long term. Even with substantial evidence, methane capture won't go anywhere unless governments and people are on board. Some methods, like using digesters on farms or plugging methane leaks from gas wells, are not controversial, but spraying iron salt aerosols is a lot more complicated. A lot of people worry about side effects and about those who control the technology, and even more about the ethics of messing with the atmosphere at all. There's also the question of governance. If a company sprays aerosols over the ocean, but the effects reach another country's airspace, there's a lot of questions about who would be held responsible for that. These kind of engineering ideas can often cross national borders, which means they need international agreements in place to make sure that it is done ethically. Groups like the ETC Group and Geoengineering Monitor have pointed out red flags, saying that this kind of tech could, quote, interfere with natural ecosystems, and that, quote, governance is poorly developed. In other words, the science is currently ahead of the politics when it comes to this method. So, no climate solution is 100% risk-free, and methane capture is no exception. Whether it's a high-tech bioreactor or a big aerosol release, things can go wrong in a lot of ways. And one of the biggest issues that we don't fully know yet is the long-term effects. For example, if ISAs are sprayed into the air, we don't know how they're going to react in different climates as they spread. They could end up warming some areas instead of cooling them, or vice versa. Um, a quote from the source Turner et al. Says the potential environmental impacts of such climate mitigation remain unexplored. That's why risk management is really important in this case. These projects need built-in monitoring systems to track what's happening to make sure that it's done appropriately. And there also needs to be, constant evaluation instead of just a one-time report to make sure it's being handled carefully. So, in conclusion, methane capture has a lot of potential to slow down climate change, especially since methane traps way more heat than carbon dioxide in the short term. Technologies like bioreactors and iron salt aerosols could help us get there, but it's definitely going to require a lot more work. The tech is still developing, it's really expensive currently, and the environmental side effects are not known yet. And plus, a lot of people and governments don't trust the process yet. We can build safeguards into these projects and monitor them to make sure it's done properly. And methane capture could be something that we explore more in the future, but currently it's going to need more development. And then the next slide here is my works cited.